Hi, so the purpose of this video is to just provide you a uh, video explanation to go along with the solution for a couple Gauss's law problems, so you have that to study for your reference. Um, and these are just a couple problems that we had looked at in class. And so the first one is a spherically symmetrical situation. So let's check this out. So the scenario that we're going to consider is a point charge Q. It's surrounded by empty space, and then it's surrounded by this metal concentric shell that has thickness from R1 to R2. And we're going to use Gauss's law to figure out what the electric field is basically doing everywhere in this configuration and go from there. So the first region that we want to consider is going to be for radius less than R1. So let me try and annotate this a little bit. So the Gaussian surface, since this is a spherically symmetrical geometry, the surface that we would use would be a sphere. Remember, we're picking this to make this calculation easy. And so this will be for R less than R1. And the starting point for all of these problems is the same, Gauss's law. So our statement E dot dA is equal to the charge enclosed over epsilon naught. So the flux through that closed surface only depends on the charge that's enclosed by it. And just to reiterate, we're picking the surface because E points radially, but a sphere also, remember the area vector points perpendicular to the surface. So both of these vectors are pointed in the same direction. Since E and A are parallel to each other, this dot product just becomes a product, E, A, and the charge enclosed in this case is just Q. So the reason for this is because E and A parallel to A. And then the next thing that we can take advantage of is, since we know that it's spherically symmetrical, we know that E at a given R is constant, so we can pull it out of the integral. And then notice this thing is just a fancy way of saying what is the area of our surface. In other words, what is the area of a sphere? And then we can solve this for E. And notice we get this expression that should be familiar to us as this is basically Coulomb's law with this 1 over r squared behavior. So that's the first surface within R1. The next surface would be within this metal. So as we move out, once we get beyond R1, it's going to behave differently. So for R 1 less than R less than R2, what's going to go on here? Well, starting point is the same. In fact, the left-hand side of this is going to be identical. But here we can notice, so what's going to happen? This is a conducting shell. And so what would happen is we know that there isn't going to be an electric field in the conductor because there will be no net charge that's enclosed in our surface in this case. So think of this as being 0. So E must be 0. And we can reason out what's going on, why this is happening like this. So we know that in a conductor the charges can move. And so if you have that charge in the middle, charges in the conductor are negative charge of Q, negative Q, is going to be attracted towards that charge in the middle. And so you can think of it as there being negative Q worth of charge spread around the inside of this. And doing that, once we're within our blue Gaussian surface, that negative Q and plus Q is going to cancel, leaving us with nothing. So if we want to think about it actually maybe more explicitly as Q minus Q within that surface, giving us 0. That's our reasoning for why the electric field will be 0 within the conductor. Okay, cool. And so let's pick our last region here. So the last surface would be outside the whole configuration. So for R basically greater than R2, outside the whole configuration. Now in this case, well, in all these cases, the starting point's the same. And just like the others, we already know what the left side is doing. On the right side, however, we have two different charges. So we have Q and at the center, and then we add to it that negative 2Q. And remember, Gauss's law, all it depends on is the charge that's enclosed in your Gaussian surface. So for this largest surface, it encloses both Q at the point at the middle and the negative 2Q. And so what's that going to give us but negative 1Q? And so E here looks like negative Q over 4 pi epsilon naught R squared. And so we've computed what the electric field will be for each of those regions. And then the other thing that we want to do is to sketch a plot of what this would look like. So let's give ourselves a little cartoon. So from from 0 to R1, what's it doing? Well, it's dropping off like 1 over R squared. So it's going to be dropping off. And then from R1 to R2, the electric field is 0. And then beyond R2, it's also dropping off, but it is negative. So we would see something like that as we get to larger R. So that's an example of a situation where we have spherically symmetrical, a spherically symmetrical configuration. So let's look at the other question. So the second of these questions is a cylindrical problem. So we're told, let's use Gauss's law to derive the electric field for all R for the following. So we have a solid, so in this case we don't have a cartoon, so let's sketch ourselves a cartoon. We've got a solid cylinder, and it has a radius of R1, and it has some charge per unit length of lambda. And then around this is a thin metal shell. Try and draw that a little bit neater. Of 2R, radius of 2R. This one, 2R1. And this is carrying a charge of negative lambda per unit length. And we're given some numbers for actual numerical values for lambda and the radii. And again, we're going to consider it in 3 different regions. We're going to compute E, sketch what it looks like, see where it's a maximum, and then actually compute what the surface charge density of the metal cylinder is. So actually, this is sort of a side sketch. Let me also draw it from the top view. This thing will just be a circle. It's maybe a little bit easier to see. Actually, this will be something like this, where we have R1 and 2R1. Okay, so all right, what are our Gaussian surfaces? Well, the first surface, so for R less than R1, and this is a solid metal cylinder. So same logic as we saw with the last example. Starting point is the same. So, and since we're inside of a metal, we know the charge is going to arrange itself such that the electric field inside is 0. So that's easy. In other words, all the charge is on the surface of the metal cylinder. Okay. For our next region, oh, and I should say, in this case, the symmetry that we're interested in is it's cylindrically symmetrical. So we didn't even need to get into it with the first one because we know immediately that the electric field is 0. But let's drill down on that here. So starting point's the same. Start with Gauss's law. Now, the argument is the same as with the spherical case, although now we're talking about cylindrically symmetrical situation. So considering our blue surface, the electric field still points radially away, but, or not but, and the area vector also points perpendicular to the cylinder, our cylindrical surface. So in other words, E and A are parallel again. So E and A are parallel. So that means that dot product becomes just a product. Additionally, since E is constant at a given radius, that means that we can pull it out. So we're just left with this. Now the charge enclosed in this case would just be lambda times the length, however much length of the cylinder we are considering. And then what is this? Well, this is just going to be the area. And in this case, instead of it being the area of a sphere, we're talking about the area of a cylinder because it's cylindrically symmetrical. So E would be multiplied by, well, what's the area of a cylinder? But 2 pi r times however long the cylinder is. And this is equal to lambda L over epsilon naught. So we can see, some stuff is going to cancel, and we're just left with E equals lambda by epsilon naught r. So it's proportional to 1 over r, and this should be, this was an expression that we could actually come up with by integrating Coulomb's law, but this is the easier way to do it by using Gauss's law. And then our last region would be outside the whole thing, our Gaussian surface. So for r greater than r2, got same starting point. Now, we're told that the charge per unit length of the outer one is negative lambda. So that means that although this side would be the same, we have lambda minus lambda times L. This will be 0. And so the electric field outside is also 0. let's sketch a plot of this. R1, 2. So this plot will be pretty simple. It's 0 inside the conductor. In between R1 and R2, it drops off proportional to 1 over R. And then outside, it's also 0. So where is the electric field at a maximum? Well, it's at a maximum at the surface of the conductor. And what will that be? So E max is going to be lambda over 2 pi epsilon naught R1. And we could compute this as a number also. So let's see, we've got 1 microcoulomb per meter, 2 pi epsilon naught. And if we compute this as a numerical value, we find that this is about 6 times 10 to the 5 newtons per coulomb. That was part C. The last bit of the question asks us to find the surface charge density of the cylinder. So let's look at that real quick. So I think the easiest way to think about this is just to relate. You know that Q depends on the linear charge density, lambda times L. Well, that has to equal the surface charge density times the area. So if we're trying to find the surface charge density, surface charge density is just going to be lambda L over the area. What is the area for a cylinder? That'll be 2 pi R L. And so notice our factor of L is going to cancel, and we're just going to be left with lambda over 2 pi R. So 1 microcoulomb over 2 pi R. And I think the metal cylinder, so you could compute it for either one, but say the metal cylinder that we're talking about is the outer one, then this would be 2 times 0.03. And if we crunch these numbers, we would find that this gives us about 2.65 times 10 to the minus 6 coulombs per meter squared. So basically 2.65 microcoulombs per meter squared, sigma. And there you have it. That's how you would compute, this related quantity. We worked with linear charge density, surface charge density, and then the other one, maybe just to mention, you also have volume charge density, where rho times volume equals Q. So it's nice to have an excuse to talk about that related issue, because that can be kind of confusing when you're just getting started with these kinds of problems, the different kinds of charge densities.